Okay. 13 says f of x equals cos of 3x. Find f inverse of 0, which equals pi over 6. Find the derivative f inverse of x at x equals 0. Oh. I want you to find that. So I threw away trig inverses. I know that it feels like we should be doing trig inverses because that's the context, but I threw this back and I just went and did all the stuff that we learned about inverses with finding your x coordinates, finding your y coordinates, finding your slopes, flipping them around. Okay. Now, somewhere, and Madeline brought this up, and I'm going to use her question as an example. Somewhere on the cheat sheet requirements, it says to do an example where you have an x and a y coordinate for the original function, and you flip it, and then you find the derivative of the original function, and you flip it for the inverse, and just to write an example of that happening. And the other day, you guys on the quiz review asked me to do, I think it was number 6, if I remember correctly, and that was an example of this happening. This is about to be another example of this happening, and this is a really common type of example, which is why I wanted it to be on your cheat sheet. Okay, so just a heads up, this is another situation where we're going to show the same thing. Okay, so I'm not going to write this down because I think I botched it. I'm going to erase this real quick. Okay, so in here we have f inverse of 0, which means that f of pi 6 equals 0. That's how inverses work, right? F of 0 equals pi 6. F of pi 6 equals 0. They told, actually I didn't botch it, they told us to find the derivative of f inverse prime, or f inverse of x, find the derivative of f inverse of x, and they wanted us to do it at 0. So they said take f inverse and find the derivative, so that's f inverse prime, and they said to do that at x equals 0, so that's f inverse prime of 0, and they said find that. That's what we're finding. So this answer is very closely related to f prime of pi 6. And the reason I know that they're closely related is because I've got xy and I've got yx, because these two are traded. That's how I know that those two derivatives have to be closely related to each other. Does that make sense? So if this is 0 pi 6, this has to be pi 6 comma 0. Does that make sense? So that means these two derivatives have to be closely related as well. Okay? I don't have the inverse function, but I do have the actual function. So I could find the inverse function, I could, but I'm feeling lazy, so I don't want to. I'm just going to be real with you. We did inverse functions all day yesterday. They were a little bit harder to work with. If I can just deal with cos, that is my comfort zone. So if I can avoid finding the derivative of an inverse cos, I'd rather find the derivative of cos than I would find derivative of inverse cos. It's just easier. It's quicker. If I can do that, I'd rather do that. Does that make sense? Okay. So what I'm going to do is I'm going to find f prime of x. What is the derivative of cos? Okay, so I'm going to do negative sign. I'm going to keep the inside the same, times the derivative of the inside. Okay, so I'm going to go ahead and clean this up a little bit. I've got negative 3 sine of 3x. There it is, all cleaned up. Okay, and now I'm going to go ahead and evaluate it at pi over 6. Okay, and that's because I know this whole relationship is happening. So they gave to me in the problem that f inverse of 0 equals pi 6, and I was able to deduce from that that f of pi 6 equals 0. They told me I wanted f inverse prime of 0. I wanted the answer from that. And based on what I knew that if I could find f prime of pi 6, that would give me some information that I wanted. Okay? So now I'm going to go ahead and find f prime of pi over 6. I've got negative 3 times sine of 3 times pi over 6. What is 3 times pi over 6? Pi over 2. Pi over 2 on the unit circle is up here. That is the point 0, 1. Is signed the x-coordinate or the y-coordinate. So it's negative 3 times the y-coordinate, which is 1. And so it is what? So it's negative 3. So my slope for my function is just negative 3. So if I do rise over run, it is just negative 3. So then for my inverse function, what should I do for my rise over run? Flip it to run over rise. So instead of negative 3, what's it going to be? Negative 1/3. That's the answer I was looking for. Now I can do it with inverse context of what we were learning yesterday, but it's not the easiest way to do the problem. Yeah. Please don't make me. Let me do it first and then show you guys so that I don't mess up while I'm doing it because I don't have it on paper. But this would be a great example problem for your cheat sheets. To show that idea of if I have the function, I have the inverse function for points. If I have the derivative, I have the inverse derivative for the same point. Yeah.
Could you use the derivative of inverses, or should you use it?
I would do it this way because the connection is direct and you have less room for error. Does that make sense?
Yeah, a little bit. It just confuses me when you like flip things.
Mm-hmm. So if we were to do it, no, I'm not going to mess with it. I can do it the inverse way, but I'm going to have to do it separately without you guys watching me, and then I can show you the other way. So I'll show you a little bit later in the period for those of you who are curious to do it the other way. I'm just not going to do it on the fly in case I brain fart. Yeah. Yes, I will, but I'm going to do it off to the side, and then I'll come back and I'll show you guys. Yeah. Okay. So what is the equation for the tangent line? If you have y equals tan inverse of x at x equals √3. So if we're going to do the tangent line, we need to have y minus the y-coordinate equals the slope times x minus the x-coordinate. We know the x-coordinate is √3, so we already have that plugged in there. So we still need to find the slope. We still need to find the y-coordinate. So do you guys want to find the slope first, or do you want to find the y-coordinate first? Slope? Okay, so for the slope, we need to go ahead and find the dy dx. And so that's what we were doing yesterday with just finding our derivative. So I'm going to go ahead and do tan on both sides. Tan. So I've got tan y equals x. And then I've got my derivative. So secant squared y dy dx equals 1. And then dy dx equals 1 over secant squared y. So there's my derivative. And now to put it in context and figure out what 1 over secant squared y is, I just need to have my triangle. So for my triangle, I'm going back to the beginning right here. Tan y equals x. So here's my y. Tan y is opposite over adjacent, so x over 1 opposite over adjacent. And I'll do my Pythagorean theorem, so my hypotenuse is c. So Pythagorean theorem, I've got 1 squared plus x squared equals the hypotenuse squared. If I solve for c, then c is the square root of 1 plus x squared. And secant is just the opposite version of cos, so instead of adjacent over hypotenuse, it's hypotenuse over adjacent. So if secant y is hypotenuse over adjacent, that would be square root of 1 plus x squared over 1. Secant squared y is that squared. And so that would just be 1 plus x squared. Are we good so far? So that means that our dy dx is 1 over 1 plus x squared. So this is one where I said if you do memorize a shortcut, tan inverse is the one to memorize. Tan inverse is just 1 over 1 plus x squared. So it would not be harmful for you to memorize that one. That one does seem to show up in multiple choice problems, on FRQs, wherever. That one seems to show up more than the others. So if you do memorize a shortcut, it should be that one. Okay, so we've got dy dx. We're going to evaluate it at root 3. The nice thing about this derivative is it's only in terms of x. It's not in terms of x and y. So we do have enough information right now to evaluate our derivative to find our slope. So I'm going to do dy dx evaluated at x equals root 3. And so I've got 1 over 1 plus root 3 squared. And so what is my slope? 1/4. Okay. So root 3 squared is just 3. 1 over 1 plus 3 is 1/4. So there's my 1/4. And then the hardest part about this one was finding the y-coordinate, right? So our y-coordinate, y equals tan inverse of root 3. So with evaluating that tan inverse of root 3, you have to remember which quadrants you can evaluate tan inverse for. So inverse functions, tan and sine inverse, can both be evaluated only in quadrants 1 and 4. Cos inverse can only be evaluated in quadrants 1 and 2. So for tan inverse, I'm picturing quadrants 1 and 4. When it's tan inverse, it's saying that the angle is the answer. So when you put a number right here, it's going to be an answer like pi halves, pi 6, negative pi halves, negative pi 6, something like that, okay? Since it's pi thirds and not negative pi thirds, that's telling me the answer is going to be in quadrant 1, not quadrant 4, okay? Since it's a tan, that means I'm taking an answer that is a y divided by x that simplifies to be root 3 over 2. Or sorry, simplifies to be root 3. So a y divided by x that simplifies to be a root 3 on the unit circle is what I'm looking for. So I'm picturing a quadrant 1 set of ordered pairs. So I've got, this is root 3 over 2, 1/2. This is root 2 over 2, root 2 over 2, and then this is 1/2 root 3 over 2. I'm picturing the one that has a y divided by x that simplifies to be root 3. So which one is it? Yeah, this one right here, which is pi thirds. So this is pi 6, pi fourths, pi thirds. So the y-coordinate there, tan inverse of root 3 is pi thirds. So the y-coordinate is pi thirds. There's your little mini trig lesson for the day. So y minus pi thirds equals 1/4, x minus root 3. So the answer should be E. Answer E. All right. First and fourth quadrant. And then the answers that are in fourth quadrant, they're not actually the angles that are there. It's not 7 pi fourths. It's not 11 pi 6. It is negative pi 6, negative pi fourths, negative pi thirds. It's the negative angle. So if you look in your summer assignment, there is a little section on that, just reviewing those. Yeah.
Is that one of the things that we can have on there?
You could put it in there. It's not technically the unit circle. If you need to have a little reminder, the way that I put it in your summer assignment is I did it like this. I said sine inverse, tan inverse, and I circled these two. And then I said cos inverse, and I circled those two. And I'd be okay with that. You can't write the unit circle in there because it needs to be memorized. Yeah, so if you need to say quadrant 1, 2, 3, 4, that's fine. For inverse, if you need to say these are the negative angles, that's fine. So like negative 6, like if you needed to have an example and say like this one is not 11 pi 6, it is negative pi 6 for inverse. Evaluating inverse, that's okay to write something like that. So I'm okay for you guys putting like little things in there to remind yourself about it. It just needs to be clear that what you're doing is you're reminding yourself about inverse trig. You're not trying to sneak the unit circle onto your cheat sheet. Does that make sense? Okay. And the only reason I'm nitpicky about that is because you have to have the unit circle memorized. So you guys are already starting to see that the unit circle pops up on problems, and we haven't really even gotten into a lot of trig yet. Once we get into a lot of trig, there's going to be a point where like cheating to know the unit circle is only hurting you. There's a point where it's like you have to have operational knowledge of the unit circle because they expect you to. So, the worse you're hurting yourself, you really just have to have it memorized. So if you don't have it memorized yet, just start, I don't know, I can print a bunch of copies and you can just start writing it out until you know it, would be my best recommendation. Yeah. I see some panicked eyes, so maybe we start doing that this weekend. Do I need to start printing copies of it? All right. Are we ready to do L'Hopital? Yes? Okay, so we figured out the thing that we need to turn in is the inverse trig. That's the only thing we need in. Is that what we figured out? Marvelous. All right, for L'Hopital, I don't think I have any more class notes to do, so then we are just looking at the assignment and getting started. Making sure that we're comfortable or with it. L'Hopital is something that saves us a little bit from the squeeze theorem. So sometimes they can phrase multiple choice questions. You have to use the squeeze theorem, but a lot of times you could like manipulate the problem and just do L'Hopitals instead, which is honestly what most people do. So that question where we have sine x over x and we had to memorize something and use the squeeze theorem with it, once you learn L'Hopital, you pretty much never have to do it again. Which is, unless they phrase the multiple choice question in such that you can't do that. But for the most part, L'Hopital becomes like our new best friend. So remind me when we are allowed to use L'Hopitals. 0 over 0 or infinity over infinity. And the one that confused me but works is negative infinity over positive infinity. They don't necessarily have to be the same sign. It still is okay, is what I have learned. Okay, so, and the one thing that we found in our very first P calculus is that if you write equals 0 over 0 and then you start L'Hopitals, they will grade you, the AP graders will, because the answer is not 0 over 0. They will go, so if they're like, oh, it was 0 over 0, therefore I'm going to start using L'Hopitals, which is like in our heads, that's what we think is like, oh, 0 over 0, so I'm going to use L'Hopitals. If you write this on your paper, they will go, oh, that's not the answer, wrong, because they're being nitpicky mathematicians. Does that make sense? So the way that we show our work is we say, oh, the top is 0, the bottom is 0, therefore we can do L'Hopitals. Do you guys see the difference there? I'm not saying it equals 0 over 0 because technically it does technically equaling something else, right? It doesn't equal over 0 in the end, it equals something at 0 on the top, 0 on the bottom. That's how we know that we can do this method, okay? All right, so let's go ahead and maybe try some of these. Is there a problem on the page that looks intimidating that you would like to do together? Yeah, arrows are great. A lot of times I put an equal and I turn it into an arrow because I forget, just like you would forget. Yep, so that's a good habit to get into. Mhm. Yeah, although I did hear you do want to show, so I think having a 0 over 0 on your page is probably fine. There was a point where they were so nitpicky that if they saw it anywhere on the page, they started marking down. I hope they're not doing that anymore because that's like over the top. But you do want to show to truly do L'Hopital's, because what they did that year at the AP grading, because the way that they grade the AP, I don't know if you guys knew this, is they like get a bunch of calculus teachers together and they get all the tests together and then they like go, they are like at a hotel and they have like the like one of the rooms rented or whatever, and they say like everybody grading FRQ1 sits here, everyone grading FRQ2 or FRQ2 sits here, and they have like a binder of acceptable answers. And what happened is there was like a huge debate. It was like a big controversy that year, and they literally went and they got a bunch of calculus textbooks to see like how are the calculus textbooks teaching it, and what they found is that not a single textbook said 0 over 0. That's what teachers were writing, but that's not what any of the books said. All of the books said the top goes to 0, the bottom goes to 0. And so because that's what the books were saying, because that's what's mathematically accurate, unless kids said that, they were marking it wrong. And like no kids said that because like nobody was writing that at the time. And then that year, that whole question, like everybody got wrong, which is unfortunate. All the teachers, when I went to the AP grading thing that year, or like the AP training thing that year, all the teachers were very upset. It was like, oh, there was lots of red faces, lots of exploding. I was a baby AP calculus teacher, and I was like, yes, we're angry. I'm gonna eat more coffee cake and take notes. Rah, 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 you know, so. But the thing that's sad about it is if teachers who didn't attend that meeting had no idea, and they just kept teaching it that way. So that's the unfortunate part. So we just have to make sure that our notation is like better, you know, is good enough that a nitpicky mathematician would not find error with it. Yeah. Okay. So let's at least do one of these, a couple of these, make sure that our notation is good, that pretentious mathematicians think that we are worthy of their time. That's what our goal always is, right? Also, did we notice this is the last lesson of the unit? This is our last learning day. Okay, so no video tonight, but the next thing that we are doing Monday is test review day. Just a heads up. Okay. All right, do you guys just want to do number 1, or do you want to find a more difficult problem to do? Number 6? Do one on the back? 12? Do number 12? Okay. Okay. All right, so I'm gonna start off with good notation. So I'm just gonna do the top and the bottom separately. So I'm gonna say the limit as x approaches 0, and if I do the top, so square root of 1 plus x minus 1 minus x over 2. What happens if you plug 0 in? Yeah, so you get 1 minus 1 minus 0, so you just get 0. Okay, equals 0. We do the bottom limit as x approaches 0 of x squared, 0. And so when we get 0 like that, we're going to say use L'Hopital's. And you can't shorten it. And the reason you can't shorten it is students used to say L. And then students started saying Lagrange, which is another mathematician that starts with L. And then they were like, oh my gosh, these students don't even know that it's L'Hopital, not Lagrange. And then they stopped letting students shorthand it. So you have to say L'Hopital. So the graders go back and forth between how specific they are. Yeah. Yeah. So we just don't short. I think you could probably write L-hop, but I'm just gonna err on the side of accuracy and just possibly, probably, but then they'd be like, yeah, do you want pancakes or yeah, what's happening? All right. Okay, so now that we've done that, what should we do? Derivative of the top and bottom. So I'm going to keep my notation because I'm not trying to kill any owls. I believe it's owls. All right, so, and this is not a quotient rule, right? We're not thinking of it as a top and a bottom where we have to do the quotient. We are literally doing just the derivative of the top, keep at the top. Do the derivative of the bottom, keep at the bottom. So, derivative of the top, how do I do the radical? Okay, so I have 1 plus x to the 1/2. And so when I do that derivative, what do I get? And then the derivative of the inside is just 1. So you can write it as a chain rule if you need to, but if you don't feel like you need to do that, that's fine. Let me try to zoom in. Just need my remote. Zoom. Okay. Derivative of -1, 0. Okay. Derivative of x over 2, 1/2. Okay, so this is kind of like saying -1/2 x. So that's just minus 1/2. Okay. And then what do we have on the bottom? 2x. I'm just doing that because that's how my brain works. Yeah, my brain needs that.
What you said that was like how you did it at the top.
Yeah, wait, how did you do 2x like right there?
Derivative of x squared is 2x.
But I thought we were supposed to separate. Yeah. That's what we're at. Yeah.
Oh, so when you do L'Hopital's, you do the derivative of the top, the derivative of the bottom. And you have to write it like that. So this is, when I did L'Hopital's, this is how I did it.
So you write them together? You don't write them separate?
L'Hopital's is you doing the derivative of the top, derivative of the bottom. Now, if I'm going to have to do L'Hopital's again and evaluate it again, I'm going to have to write this out again. You could write the derivative off to the right. Yeah. All right. So what are you guys noticing? I'm going to clean this up a little bit because this is hard for my brain. So I'm going to say the limit as x approaches 0. For the top, I've got 1 over 2 square root 1 plus x minus 1/2. I got 2x. And then, now what happens if I do the 0 again? 0 on the bottom, what happens on the top? You get 0 on the top? Okay, now we do have to show our work the same as we did last time. Wait, what happens when you plug 0 in right here? It's the square root of 1. So it'd be 1 over 2 times the square root of 1. So it'd be 1/2 minus 1/2. Yeah. So we're still going to get, the top has a limit of 0, the bottom has a limit of 0. We're going to get L'Hopital's again. Okay? But we can't just say 0 over 0. They don't like that notation. We have to write it out again. So, and this is what we're messing with here is we know we need to use L'Hopital's, but we have to have correct notation all the way through. So the correct notation is we use L'Hopital's. This is us using L'Hopital's, but we're trying to make sure that we satisfy the need to have perfect notation. So the perfect notation is limit as x goes to 0 1 over 2 square root 1 plus x minus 1/2. That is 0. Limit as x goes to 0. 2x, that is 0. Use L'Hopital's. If one of them is 0, you can't use L'Hopital's. So if the top was 0, then we would say, oh, the limit is 0. If the bottom was 0, we'd say, oh, there's a vertical asymptote. And maybe the limit is positive infinity, maybe the limit is negative infinity. So we're kind of, this is, in a little bit, this is taking us back to Unit 1. The reason this didn't belong in Unit 1 is because we had not learned derivatives yet. Does that make sense? Okay. It's a two-step L'Hopital's problem. And we're still not done because we got 0 and 0 again. All right, so now we're taking the derivative again. I'm not going to take the derivative of this one because that's hard on my brain. I'm going to think of taking the derivative of this one. Are we comfortable with that? Okay, so I do have to show my work. So I'm going to do the derivative of the bottom because that's easiest. So the derivative of 2x is 2, okay. Now the derivative of the top negative 1/2 minus 1, negative 3/2. And if we were to multiply by the derivative of the inside, it would just be 1. So the chain rule is a chain rule, but it doesn't really make a difference. And then the derivative of negative 1/2 is 0. Okay. Say that again. I use this one right here because it was easier on my brain than this one. So these are the same. They're the same, yeah. I just used this one because it was easier. Okay, so I'm going to go ahead and clean this up. It makes me feel like sighing too.
Wait, it's a lot to write out.
Yeah. Yeah, it's the square root of 1 plus x and then to the third.
How do you know if the third is on the inside of the square root or the outside?
It's both. It's however you want to write it.
Oh.
So you could do 1 plus x to the third and then the square root, or you could do the square root and then to the third. It's the ease with which you can write the number. So I alternate depending on how I feel like I'm going to want to plug it in. So. Okay. So I had this first and then I went ahead and bumped it down with the 2. Are we comfortable? I feel a little bit like I want to vomit, but aside from that, totally comfortable, yeah. Yeah, pretty good, pretty good. All right, so now when I plug the 0 in, I get the square root of 1 plus 0, which is 1. Okay, so the square root of 1 is 1. I get 1 cubed, which is 1. Okay, so I get 1 times 8, which is 8. Okay, so I got negative 1 over 8, which is, okay, there we go. So thank goodness I didn't say it was 0 over 0, because it's not. It's negative 1/8. That's why the mathematicians are not okay with me saying 0 over 0, because the answer is not 0 over 0, it's 1/8. Negative 1/8. So 0 over 0 is an indeterminate form. So the indeterminate form tells you, oh, direct substitution is not good. I'm not done. 0 over 0 tells you, oh, there's a hole. I'm not finished yet. I have to do another method. The other method I have to do is L'Hopital's. Oh, I still have a hole. I have to do another method. L'Hopital's. Oh, my answer is -1/8.
But why does it work to find the derivative?
I don't know. That's a question for the Google. Yeah.
Okay.
Yes.
So don't use the L'Hopital's again.
Yeah, you don't use L'Hopital's again because, so remember when we were doing that first unit, how we would try to do direct substitution and it wouldn't work? And that would tell us to use one of the other methods. It would tell us to expand, it would tell us to factor, it would tell us to do something else. But then as soon as we got stuff canceling and we could do direct substitution, we would. It's the same thing with L'Hopital's. So what we did is we added another method into our toolbox. So we have expand, we have factor, we have conjugate, we have undo complex fractions, we have all those things we used to have, but now we have one extra one, which says that if it's 0 over 0, or if it's infinity over infinity, we can do L'Hopital's, and that we're going to keep doing it until we can plug the number in and not get that. So as soon as we saw this 2 on the bottom, we knew that we had to be done with L'Hopital's, because as soon as you have that 2 on the bottom, you're not going to get 0 over 0 anymore. Does that make sense? So as soon as we took that derivative and got the 2, L'Hopital's had to be done. No matter what, L'Hopital's was over at that point. You're done. So when that 2 was there, L'Hopital's was finished. Okay, do you guys want to do another one? Yeah. Now, so some of the methods that we learned before could still possibly work. For example, in Unit 1, we didn't know how to do L'Hopital's, so we never would have tried L'Hopital's on that problem. How would we have done number 8 in Unit 1? Yeah, we would have done the conjugate. Okay, the conjugate still works. So if you wanted to do the conjugate on number 8, because you're like, this L'Hopital stuff is BS and I don't feel like doing it, then do the conjugate. You'll get the right answer. Okay? If you tried to do direct substitution and you got 0 over infinity, L'Hopital's will not work. If you tried to do direct substitution and you got infinity over 0, L'Hopital's will not work.
And then if it's not matching, then you can absolutely use it versus you can.
So a lot of the problems in Unit 1, there were a lot of them that were 0 over 0. So there were a lot of them we could have used on. We just didn't know L'Hopital's at the time.
Okay. This one just did it. I give them infinity over infinity.
Mm-hmm. Yeah. Yeah, it doesn't seem to. I wasn't sure about that. That's one we might Google. But as I've done L'Hopital problems, they seem to always be the same sign for other problems. As I've done complicated problems and weirdo cases, it seemed that this doesn't matter. That it ends up being okay. All right. Let's find another problem to do just to make sure that we're okay with notation and stuff like that. 10. Okay. All right, so this time, this is good. We're plugging in infinity, not plugging in 0. So how would we have done this one before? End of the infetable. Okay, so we already know the answer to this one. What's the answer? Based on end of the infetable, which side wins? The top wins. So based on end of the infetable, the top wins, and our answer is going to be infinity. Okay, so we already know the answer, the infinity. Now let's go ahead and do this using L'Hopital's and just confirm that what we knew from end to the infetable is going to work. Okay. So with L'Hopital's, if you plug infinity in on the top, what do you get? If you plug infinity in on the bottom, what do you get? Okay, so now we're going to go ahead and show that. We're going to say limit as x goes to infinity of e to the 2x is infinity. We're going to say the limit as x goes to infinity of 2x squared is, and we're going to say, okay, conclusion, use L'Hopital's. As an answer, you just can't use it as a number. Yeah. This we would also say like, oh, D&E unbound. Okay. And then we would take the derivative of the top and the bottom. Okay, so what's the derivative of the top? Yeah, so e to the 2x times 2, because the chain rule, over 4x, and we'll go ahead and just rewrite it. Yep. Yeah, mathematicians are so pretentious. They just really like their notation to be perfect. Okay, what's happening again? The top and the bottom are both going to be infinity. But can we just do that in our heads? We got to write it down. Oh, these people.
So why do we like say use L'Hopital's after we've done it? I mean,
This is like justifying your use of L'Hopital's, but but stating that you're going to use L'Hopital's is like the idea of the formality of like using a sentence to say it. It's also showing recognition that you're using L'Hopital's and that you know the name of it, as opposed to I'm just doing stuff and I don't know what I'm doing. Is the derivative part, yeah. Yeah. The knowing that both are infinity and that it's appropriate to use it is the justification piece. But the derivative part is actually using L'Hopital's. Yeah. Okay, and thank goodness we are to the next piece, because what's about to happen? We're about to get a 4 on the bottom, which is putting a stop to the madness. Are you guys excited that we're putting a stop to the madness?
Yes.
4 on the bottom. Okay, what do we have on the top? 4e to the 2x. Yeah.
Can, like, if you rewrote the limit, should you rewrite the whole thing of, like, limit as x goes to infinity of 4e to 2x, and then limit as x goes to infinity 4? Is that illegal, or could you technically write it? You complicate it. I don't know if that makes sense.
You would rewrite it as what?
Like, you would rewrite both the limit pieces of the top and bottom with that. Or could you not do that?
Rewrite the top. You could find them separately. That's like the property of limits, is that you can find them separately, but you don't need to. Yeah. Yeah. Yeah, some people kind of get in a rhythm where they just keep finding the top and the bottom separately and then go, oh, I'm done. And then kind of back up and say, oh, that's the answer. And you're able to do that because property of the limits tells you that that's allowed. Yeah. All right, so at this point, our limit is what? Infinity. And oh, we're just done. And we can say D&E unbound. You do not have to write D&E unbound. It seems that a lot of the AP graders are interested in this answer because they want to know if it's a positive infinity or a negative infinity, and they're not as nitpicky about you saying D&E unbound. They're not as worried. They won't mark you down. They're not as worried about that. if you just say D and E unbound, then they're like, well, I wanted to know which one. So they kind of like for you to say which infinity, so they know which one. If you just say the infinity, they seem to be fine with that.
Okay. That's what we were asking maybe like have on a test, just like this problem that
Uh-huh.
check that it would be 0 over 0. Does that mean that
I'm gonna talk
like
first.
use L'Hopital
Uh-huh.
or use it first?
It means you can. So hey guys, we had a really good question. So when you see a problem like number 8 and you notice that it's 0 over 0, does that mean you have to use L'Hopitals, or does it mean you can use L'Hopitals? It means you can. It does not mean you have to. And what we've started to figure out in math is that there are a lot of different methods, and some of them are easier than others, but all of them are permissible. So sometimes you might be kicking yourself later because I went quickly to an answer because I have more math experience, and so I can see the 5 different options and I can choose the best one, whereas you can see 2 of the options and you chose the one you liked, and maybe that one wasn't the fastest one. But we all got there, and so we all win in the end. Does that make sense? So L'Hopitals is added to your toolkit, and if you see it, then you use it. And if you don't see it, you might kick yourself because, oh, that was the easiest method. But the more often you see that as an answer choice, then it will start to get in your head as like, oh, yes, I could have done that, and you'll use it more in the future. Does that make sense? You don't have to use it, but you'll see it. You'll see it on an FRQ where you don't have enough information to possibly do anything else. Because, for instance, they'll put something like this, but they'll put like f of x in the problem. They'll say, like, on the top, it'll say, like, the limit as x approaches 0, and it'll be like f of x minus 2 over x. And in the problem, you'll know what f prime of x is. And there's no way you could expand that. There's no way that you could factor that. There's no way you could do a conjugate. And you'll be like, I have to use L'Hopitals because there's no possible way I could have done that problem any other way. And you'll just know, you'll be like, that's got to be L'Hopitals. And because you'll have enough information, you could plug 0 on the top, and you'll be like, if I plug 0 in, I get 2 minus 2, and if I plug 0 in on the bottom, it's 0. You'll just look at it and you'll go like, it's got to be L'Hopitals. There's no other way to do it. So there's problems like that where they force you into L'Hopitals, or else you just don't know how to do the problem. So they can kind of force you into that, and that seems to be what happens on FRQs more often than not, is that they force you into the method they want you to use. But sometimes there's multiple methods and you can choose the one you want to use. Yeah, I'd say the times that I've seen L'Hopitals show up on an FRQ, they've kind of forced you into that method. Yeah. They don't often say do it this way because they don't want to give you a hint on how to do it. They want to see what you know. So a lot of times they won't tell you the method to use. They'll see if you can figure it out. Yeah. Okay. Any other questions? Nope. Okay, I'm going to go ahead and put the answer key on the wall for you guys. And then I'm going to come around and try to get caught up on checking homework.